Good afternoon from my side. I'm Clemente Fuggini. I'm working for RINA and I'm the project coordinator of SecureGas. So today we are here with this afternoon session of our live streaming from Chivasso near Turin in Italy at the Eni test side for SecureGas. So I'd like first of all to thank all the colleagues of the project that are on site today and that have made through a lot of effort this demo possible in today afternoon. And I also like to thank all the attendees that remotely are joining our live streaming. And I hope you will find what we are showing today interesting enough to then go ahead with the contacts with us and see the perspective of exploitation of the SecureGas results. So I have a very short presentation and we can run through it just to introduce a bit to you the project. So we can go to the next slide. Thanks. So luckily, I'd like to mention that SecureGas kicked off really 2 years ago exactly this day, so the 9th of June 2019. It was in the Milan office of RINA at that time. And at that time, we were 50 persons physically attending the meeting, and we enjoyed the 3 days kickoff meeting very well. So today I'm happy to see people in the field physically present because it's also a sign that we would like to show and our commitment despite the heavy period that we have faced in the last months. So SecureGas is not finishing today. Also, we have a few months to go until the end of November of this year. As you can see, SecureGas is a consortium of 21 partners. I have the honor of coordinating them as project coordinator. And as you can see, we have 20 other additional entities. Some of them are today present on site. Leonardo, Eni, RINA as well, my colleagues, and ADPM, since they are deeply involved in the test case today. But I'd like also to mention to all of you that we have a stakeholder engagement process in SecureGas, and we have so far registered into our stakeholder platform 28 external stakeholders from 12 member states, including 10 oil and gas, I would say, and gas operators. Here you see some logo. So I really hope that after also these events and these meetings, more would like to join our stakeholder community, and that will grow with the idea of sharing the practices and the knowledge of SecureGas, and of course discussing potential exploitation of the project outcomes. So SecureGas, as the title says, it's quite self-explaining. So security of the gas network, the European gas network. Of course, we cannot tackle the more than 100,000 kilometers of gas pipeline. We select the 3 specific cases and target areas: one in Italy, one in Greece, and one in Lithuania. The one in Italy is the one clearly we are today. But not only security is a keyword of SecureGas, the other keyword is resilience. As you know, resilience is a word that has been quite a lot used in the last years, I would say, and now it's entering in our common languages since every country is now working on their, I would say, recovery and resilience plans after the COVID. However, resilience has a specific meaning, and for us in SecureGas, it has a specific. And I will say a few words about this later on. So what are the key points, key selling points of SecureGas? So why this project should be of interest to the community and to the funding authorities? Because SecureGas is a business case driven project. We mean with this that it has been designed since the beginning, so since the requirements and specification, by the end users, so the energy companies that are in our consortium. Once more, Eni from Italy, DEPA and EDA from Greece, and Amber Grid from Lithuania. And so this is sorry, if you can go back. And this is an element that is fundamental for us to ensure a potential replicability and application of SecureGas in the real operational conditions. So that's important, and as well as it is important that the fact that to cope with the requirements, we have developed a set of solutions, and these solutions are validated in the 3 business cases through demo sites and test case against KPIs which have been once more defined by our end user in the consortium. So next. But as I said before, resilience is a word that has been quite a lot used and is now a common word in our language. Moreover, the Commission recently launched a proposal for a new directive on resilience of critical entities. So I'm happy to see that this word is really associated to our critical assets and critical infrastructures. But resilience means something that need to be put in engineering, let's say, meaning to be applicable to the protection and resilience of critical infrastructure. And basically, resilience for critical infrastructure and for us means to estimate the impact of losses of functionalities on the business and service continuity. So you have a normal service, you have an event, you have a drop of service, and then you have to restore it in less time and less cost as possible. The area surrounded it is the resilience capability that you as asset owner, as operator can have. But this is not enough to be able to make that an engineering concept. We need to link resilience with the processes that asset owner and operators are currently putting in place, are currently working on. And therefore, we linked in the project the resilience concept and idea and its engineering version with the processes, the KPIs of asset management. And embedding a resilience concept and meaning into the asset management process, we think makes much more easier or helpful to the operator to integrate these concepts into real operational environment. What are the problems that we are facing in SecureGas? And you will see today some example of how we are tackling it. On one side, we have the physical, let's say, threats or incident. On the other side, the cyber one. For what concerns the physical one, there is a huge, let's say, cases of physical incidents to the gas network and pipelines reported since the 1970 by entities such as AGIG, and the 3 main causes are external interference, corrosion, and ground movement. The first one and the third one have been deeply taken into account in SecureGas, and you will see an example of what does it mean today in the demo you are going to see later. Concerning the physical part, clearly the number of physical incidents is much less if compared with the cyber incidents. Is much less if compared to the physical ones. However, and the recent event at the Colonial Pipelines in the US recall us this, the impact of these events is quite high, and the financial and reputational damage and the damage on business and service continuity is quite high. So that's clear, and it's not me to say, that cyber threats have a huge potential impact also on the oil and gas sector, and therefore needs to be considered. And we have done this in SecureGas, also trying to correlate physical events correlator engine or machine that will be shown also today as well. And to go a bit towards the conclusion of this introductory part. So clearly, we need to have a solution to tackle these type of problems or issues. And we have developed a set of solutions. We call it extended components, meaning that the technical providers in the consortium brought into the project already existing solution or components at different technology readiness level, of course, and they have improved, adapted, customized in SecureGas to the specific needs and requirements of the end user. And they have now in the phase of validating them against, as I said, the end user KPIs. We have basically 4 categories of components. We have one category that belongs to the decision support and situational awareness tools. We have one category that belongs to information management and information sharing, one that is dealing with the detection and capacity of early warning features, and one more that is dealing also with the fact of communicating and sharing the proper information not only to authorities but also to the population in the vicinity of the installations. And for gas pipeline, as you can imagine, this is clearly a very important issue as well. The components will be or have been already or are to be validated in 3 business cases. The one in Italy, so the ones we are talking about today, and the ones you will see the demo today, hosted by Eni. One in Greece, hosted by ADPA and ADA, and one in Lithuania, hosted by Amber Grid. And then this is my last slide. So I'd like to thank really all of you that are physically and remotely present today to these events, and I hope you will enjoy the demo. And now I will pass the floor to my colleague from Leonardo in the project, Rosanna Grimaldi, who is the technical coordinator also of the project, and she will go into details a bit more with the architecture and the components that will be shown today. So thank you very much from my side.
Good afternoon. I'm Rosanna Grimaldi from Leonardo Cybersecurity. I'm the technical manager of SecureGas. In this presentation, I will try to explain the technical solution that we build in this project, especially its application in the Italian business case. Let's start with SecureGas architecture. Architecture is the general approach that we propose to address the protection of critical infrastructure. Start from the bottom. In the field layer hosts the system aimed at detecting the events on the infrastructure. The 2 different colors, light blue and green, means end-user systems, that is, systems already operating in the infrastructure, and system provided by the industrial partners of the consortium. The upper layer, normalization correlation layer, aims to capture, to acquire the heterogeneous data coming from the field, and if it is possible, to correlate them. Correlate means to get more additional information from the system on the field. All the information are available to the user through situation awareness. Situation awareness means make available to the user a unified, integrated vision of what's happening on the infrastructure. This enables and decision support, the ability, the possibility to the user to identify the best action to address what's happening in the infrastructure. The upper layer, diffusion layer, refers to the need to communicate with external stakeholders when something important occurs, for example, civil protection, police, fire brigade, according to the procedure identified by the infrastructure owner. This slide lists the threats addressed by business case 3. Third-party interference is the object of this demo, and you see in a few minutes, but we also, in a simulated environment, addressed geohazard to assess landslide stability along pipeline routes, and SCADA network monitoring to detect cyber intrusion in the network. This is the business case 3 process. Just a few words on each system involved in the business case 3. EVPMS is the system patented by Eni to detect TPI threats and to detect leaks. It's based on vibroacoustic sensors placed on the pipeline. Distributed acoustic sensing, the system is provided by RINA. It performs the same duty, the same job of EVPMS, but with a different technology based on optic fiber along the pipeline route. Geohazard assessment is a tool provided by RIMA. It calculates the risks of debris flow in Pollein area. Is an area in Val d'Aosta region subject to this kind of phenomena. Geohazard exploits information coming from CALM, which is a short-term meteo forecasting station provided by Eni. All the data, information, events, alarm from the field are sent to the safety and security platform provided by Leonardo, which acquire the information and provide to the user a situational awareness. That is a unified, integrated vision on what is happening on the infrastructure. This enable and decision support, and in this demo we'll see that one of these decisions is to send the drone for inspection and patrolling duties. Now I dismiss the role of SecureGas technical manager, and I take the role of Leonardo Cybersecurity as a provider of safety and security platform for gas critical infrastructure. You have just seen the platform in the big picture of the whole business case 3 process. This is a focus on the sub-components on the platform. We start with Auditor. Auditor is a system based on deep learning, able to identify and classify environmental noises, as noises from agriculture machinery, human voices, noises from motorways, railways. How do we use Auditor? I've just mentioned systems for leaks detection and TPI detection. These systems are operating in very noisy environmental. This site in Eni is a good example. The pipelines are under cultivated field. Nearby there is motorways, railways, and this situation can cause false alarms. When an alarm is generated, Auditor classify the noise in the environmental noise, and the correlator attributes a severity to the alarm. For example, if the platform receives a vibration alarm, but the auditor classifies a noise from agricultural machinery, the severity of the alarm is lower, because the agricultural machinery probably create vibration, but these vibrations don't harm really the pipeline. In other situations, the severity can be raised. The alarms, the events, their attributes are sent to the user interface. I don't tell you anything now about user interface because in the few minutes you can see it operating during the demo. Just a few words about SCADA network monitoring. We can't protect a critical infrastructure without an effective monitoring of SCADA network. Leonardo is developing several technologies to monitor industrial networks. In this project, we brought a technique based on behavioral model. Behavioral model is a model fed with data coming from the sensor on the infrastructure. During the training phase, the model builds the correlation between variables and parameters, so during the monitoring phase is able to detect also small deviation. This is a data-driven approach that enables condition monitoring, able to detect intrusion on the SCADA network. For example, this technique is able to detect man-in-the-middle attacks, but also enables health monitoring that could because deviation of parameters could harm the pipeline. My last slide, I like to show you a picture. This is a picture of the physical test bed that we built in our artificial intelligence laboratory. It's a model, but with the real components. We had valves, flow meters, pressure meters. We have a real SCADA system and also a digital twin. Digital twin is very interesting to perform a penetration test and attacks that normally are not, of course, possible on the real infrastructure. That's all on my side. I hope we have more occasion to deep this very interesting topic. I leave the floor to Paolo Corvaglia from RINA for a focus on distributed acoustic sensing. Thank you for your attention.
Thank you very much, Rosanna. So I will briefly talk you about the DAS system, which is the acronym for Distributed Acoustic Sensing. So we are talking about a distributed monitoring system, which means that the physical parameter of interest is measured virtually at each point along the sensor. The sensor in this case is an optical fiber, a standard telecommunication optical fiber, which is laid down for tenths of kilometers along the pipeline, and which is converted by the DAS technology into an array of thousands of virtual microphones, so allowing real-time monitoring of acoustic events which are happening close to the fiber, which is the physical principle behind. The interrogator injects a pulse of light into the fiber. Then the sound waves, which are pressure waves actually, locally deform the optical fiber, so inducing some very teeny changes to the light path. And from the analysis of these changes, we can, let's say, trace the features of the acoustic event which causes the perturbation. So as all the sensing technologies based on optical fibers, also the DAS has the big advantage of not injecting any electric power into the sensing length, into the sensor. And this is why this technique is intrinsically safe and so very suitable for use in environment with high risk of explosion or fire, like in oil and gas environment. For the same reason, the sensor is immune to electromagnetic noise, and it has also a very good time stability and a very low signal attenuation, which means that with a single interrogator we can monitor up to 50 kilometers of line. And finally, the sensor is characterized by very low intrusiveness because the system can exploit already existing optical fiber infrastructure, which is very often pre-installed adjacent to the pipeline for communicating, for transferring data, like it is in this case, in this demo case, actually. So the DAS component is then able not only to detect, but also to classify, so to distinguish different possible third-party interference actions, and to send proper alarms to the operator where needed. The classification is based on machine learning algorithm and on machine learning, let's say, engine, which is fed by real data that we gathered on the same field, the same pipeline on which we applied in what we call the calibration step of the system. This functionality can be, let's say, performed along tens of kilometers, as I said, in real time and with a very good spatial resolution, which is usually below 20 meters. Just a more precise statement regarding the alerts sent by the system. In this project, we maintain quite a high level of sensitivity to the DIS system in order not to miss possible important events. The drawback of these is that we can have even many alarms and even some false alarms. But here is the role of the correlator developed by Leonardo, which some way acts as a filter because it correlates the alarms from the DIS system with the possible alarms coming from other systems. So when, let's say, when an alarm comes from the DIS, it is shown actually to the operator, but it is maintained, let's say, at a quite low degree of severity. Instead, when a correlation is detected with other alarms, the DAS alarm is some way validated, and so the operator receives a sort of complex and complete alarm, including also the correct information on the degree of severity of the alarm, which is a function of the correlation degree among the different alarms received by the different systems, let's say. So that's all from my side. Thank you. I think I will leave the floor to my colleague Francesca. Thank you.
Good afternoon, everybody. I'm Francesca Iuele, and I'm going to talk to you about the geohazard assessment component. As already stated by my colleague in the introduction, the landslide monitoring tool is able to predict upcoming landslide events and generate an early warning useful to address pre-event mitigation and schedule post-event inspection and maintenance activity. This approach is applicable to significant pipeline lengths and provide geohazard alerts based on the comparison between the rainfall thresholds and forecasted rain data. So this slide is focusing on the workflow at the basis of our tool. As you can see, we can distinguish mainly three phases. The first phase is the so-called data collection phase, and at this stage, we try to acquire the best knowledge of the phenomenon at study. Then there is the so-called hindcasting model definition, and in this phase, first the rainfall thresholds are defined. We can say that a rainfall threshold is an empirical law aimed at identifying a critical rainfall, a rainfall that can produce a landslide event. In this stage, we also define the possible landslide propagation scenarios based on the hydrological model at the area at study. And finally, we come to the third part, the third casting part. And at this stage, we distinguish two kinds of early warning 1 and early warning 2. Early warning 1 is issued when the meteor forecast, the rainfall forecast, exceeds the rainfall thresholds. And when this happens, early warning 2 adds a new level of information, which is the most suitable landslide propagation scenario, always based on the meteor forecast. So, and that completes the workflow explanation. In the next slide, I'd like to show you a flowchart that outlines how the tool was implemented in RINA Cube. First, you can see that rainfall forecast data for the area of interest, Cassandra are retrieved by Calm HD system provided by Eni. So the tool in RINA Cube automatically retrieves rain forecasted data and processes them. If rainfall thresholds are exceeded, the tool sends an alarm notification. At the same time, the tool is able to identify the most suitable landslide propagation scenario among those previously computed and stored in the database. And it sends the drone a set of coordinates that can be used to launch an inspection. So this was the architecture of the tool at a glance. I thank you, and I leave the floor to my colleague for the next part.
Hello, I'm Luca Brizzi from ADPM Drones, and with the next slides, I'll quickly present the solution for the automatic drone management system developed by ADPM Drones. Okay, thank you. As you know, the next slide. Sorry. Okay, thank you. As you know, the drones can be used efficiently in multiple scenarios that we have divided in some macro areas like safety, telecommunication, insurance, infrastructure, and agriculture. And we can summarize them in monitoring and safety. For the SecureGas project, drones are used for the operational scenarios highlighted in green here, including security, anti-intrusion, and asset monitoring. Next slide, thank you. Okay. In these slides, you can see some pictures of the on-field installation of the drone automatic management system and a couple of shots taken with optical and thermal sensor installed on board of the drone during automatic operation following some events detected by the safety and security platform. Thank you. We have integrated for the SecureGas project the Leonardo Safety and Security platform and the drone automatic management system developed by ADPM Drones called Hangar. In few detail, the automatic drone deployment solution called the Hangar allows the storage of the drone during inactivity periods, recharges the drone batteries, and manages the drone operational workflow, like opening and closing the system, weather analysis, operating condition check, and the integration with national UTM platform like D-Flight, and as well as allowing an extension of the operating range. Thank you. Behind the hangar system, there is a communication architecture, both with satellite and terrestrial system, and data management that allows its integration in the different operational scenarios and the business and application procedures. Thank you very much.
Hi everyone, I'm Simone Cesari and I represent with my colleague Giuseppe Giunta Eni in this SecureGas project, Business Case 3. First of all, I'd like to spend some words about the pipeline we are deploying the SecureGas infrastructure. We are in northwest Italy between Chivasso and Aosta. The gas pipeline is more or less 100 kilometers long with an internal diameter of 16 inches. The pipeline was formerly used to transfer crude oil, but after 2015 it has been inertized and filled with nitrogen and at about 6 bar. For SecureGas business case, we have, let's say, subdivided this pipeline into two sections. The southwest section, we have used it for the scenario of third-party interference and leak detection. The northern part, towards Aosta, let's say, it has been used to host the geohazard scenario. Okay, these slides represent the architecture of SecureGas for business case 3 with the formerly presented 4 layers by previous colleagues. And now I would like to spend some words about the technologies provided by Eni here. They are represented in the field layer, of course, and I'm talking about EVPMS, Eni Vibroacoustic Pipeline Monitoring System, and also EKMF, Eni Cassandra Meteo Forecast. The first one, it is used for the detection, localization, and classification of third-party interference, and also the detection of leaks. The physics below this patented technology uses vibroacoustic sensors that are distributed along the pipeline at relative distances of some kilometers. And the waves are registered by this sensor while the fluid and the pipeline itself act as a guide of this propagation of wave. The waves are, of course, generated in the ground all around the pipeline. For example, when a machinery digs the ground around the pipeline, or even when the machinery heats the pipeline itself. With this type of events, the waves are generated, are transmitted to the shell of the pipeline and also to the fluid, and then they propagate along the pipeline. What is important here to see is that EVPMS is able to detect and classify the event we are talking about. So, I mean, the EVPMS is able to say if we are experiencing an intrusion, an excavation, or an impact, or even a leak. The second technology here I would like to show is Eni Cassandra Meteo Forecast. It is a calm HD model for northwest Italy. It is a 60-hour forecast model, and the model is able to predict temperature, wind, and precipitation, and of course correlates this forecast with the data measured from public station and also from two weather stations that we installed here in Chivasso and also in Aosta. The file of the weather forecast are provided, are transferred to RINA geohazard component for the geohazard assessment. Okay, business case 3 has been developed in 4 stages. After a feasibility phase, we had a calibration phase. So we performed a first test campaign last October in order to acquire some data and to calibrate the system, the field layer system. Then we validated the results in a second test campaign. We brought on the field all the components that my colleagues previously explained. And here today we are going now to see the live demonstration of the full-scale scenario for TPI and leak detection. Okay, this slide is important and is referred to the third-party interference and leak detection scenario, and it lists all the tests that we performed previously, but also some of them will be repeated today. Okay. Some minutes ago, I said that the classification is very important. Here we see in the table 4 different classes of events, and they are quite different, the event and also the signal correlated to these events. So starting from the first one, third-party interference, excavation, digging, is the first action that someone that is entering and approaching the pipeline performs. So, for example, an heavy machinery approach occur. Then, for example, we have a mechanical excavation. We used a 6-ton and also a smaller excavator, and then we finished with a manual excavation. While I'm speaking at the test site, my colleagues are starting the excavation activity, because the excavation takes some time and it's a prolonged event. So we need some time to reach an alarm for a VPMS. This is because the VPMS knows that the excavation event is not very, very severe. So it sums several events before giving the alarm. So that's why we are now starting before I've finished. The second class I would like to show is the third-party interference impacts. That means we have put the pipeline at the light, let's say, so it is exposed. And now we are going to heat with different equipment the pipeline itself. So we see in the slide, we used a hammer, we used a weight dropping on the pipe, and also we used a pendulum. You see the related energy with this event. And today we will see a pendulum impact event. We will launch the pendulum at a height of 150 centimeters that correspond to 750 joule, which is a medium range energy. Of course, we cannot exceed those energy not to damage the pipeline. Impact events are more severe because they could cause an incident to the gas pipeline. And of course, the third class is even more severe. It is the detection of any leaks. So today, and in the previous campaign, we performed some simulation of leaks. So let's say control the leak with some nipples of different size and different shape. And of course, the alarm coming with the type leak detection will be treated as the most severe. And we will see afterwards. The fourth class is the sensor intrusion, that is a sort of sabotage that a thief or any people could perform going to the pipeline and damaging the EVPMS sensor system. So we are able also to detect those kind of events. All these four classes have different time responses. That's why today in the demo we will have some time to answer, to wait the alarms that will come to the DSS system. Okay, this slide. Let's say, let us see what we are going now to see at the test site. The first event will be the excavation, and afterwards the pipeline is exposed, so we will perform a pendulum impact directly onto the pipe, and the third event we will show will be a controlled leak. I didn't say before that a leak could occur in case of corrosion, of course, of the pipe, but also as a consequence of the impact. So we will see three different events with different severity. Each event will trigger an EVPMS alarm, and the alarm will be correlated with environmental audio and also the alarms coming from the AS system. All these correlated events will go through the DSS system with the classification of severity and also a geolocalization. Depending on the alarm severity, different workflows will occur, and my colleague that acts as an operator in the control room will show afterwards the possibility of action to choose. The last slide I want to say just an info. In the platform you will find a questionnaire that it is of course not mandatory, but it is important for the project as a feedback, so I ask you to fill in. It's quite fast, and to return the questionnaire to the email linked here and also in the file itself. I think I'm finished. Now you will see we are setting the cameras here, so maybe 2 minutes of a video that was previously registered from the drone in the last campaign. So enjoy this video, and then we will come online directly with the control room and the test site for the demo. Thank you so much.
Good morning. My name is Roberto Reina. I am the responsible of the development for command and control application in Leonardo. And I'm going to introduce Leonardo platform for customized for this application. It is a special application for SecureGas for pipe control, as explained by my colleague before. We are to take in consideration 3 different cases, business case. One is related to excavation. The second one is related to impact. And the third one is related to leak of the pipe. Normally, we configure this control system using 3 different screens. The main screen is the screen where you have the possibility to see all the resources on the left side of the screen. You can have 2 different squares with the map. The first one is the map where the operator can work and can see the different elements present, in that case, on the area of interest. Normally, you can see the cameras, the pipe, the people working with a tablet, and the drone. That is one of the critical elements of this solution. You can see in which way you can manage the georeference system, where you have the map of the different building, and you can configure the different layer, and you can select the layer depending the usage of the operator want to do in the different situation. You can see that the system is able to collect the event coming from the field, arriving on the screen, and collapse depending on the zoom of the map. Clicking on the collapsed alarm information, you can see all the event on the map. The same information related on the event are available on the right screen, the screen 3, and you can see different events coming from the field. For this simulation, we take in consideration 3 different type of event with different level of different critical level. We have the yellow bullet, that is the event that are not critical at all. We have the orange with 3 number of critical level. That means that you have a situation that you have to manage, but with a probability of attack that is in principle low. After that, you have the critical level 1, where you have a high probability of attack, and the bullet became red. In our simulation, the excavation is orange, is a critical level number 3, while the impact and the leak situation are critical level 1. You can select the color, the color of the critical level of the alarm, so you can see the different event in function of the date, in terms of last date, or in terms of critical information, or in terms of let me say, in terms of status, because the operator have the information related to the status. That is normally you have two different level, the new, when the event arrive from the field, when the event is taken in management, is a change in managed status. After that, you can close the event, and you can write note related of the management of the event if you want, and you can close everything. On the left side, the third screen, the operator can see the cameras that it can select directly from the resource tree, and it can drag and drop the information with a fixed or PTZ camera or camera coming from drone. In that case, from the PTZ camera, the operator can manage directly the camera using or a joystick, a virtual joystick of the screen, or in other application we use the joystick directly externally respect on the PC workstation. Now we go to introduce the last element of the system that is related to the our mobile solution that we see in use in the first scenario. This solution is a mobile application that in this configuration we will use on a tablet that is in the screen. The application, the app support the login on the system, so the only people with the right level of functionality can work with the application, and he can, the people on field can manage the camera, can see map, can manage workflow, and can send alarm. In terms of cameras, the people can see different camera, and clicking on the camera, he can see directly on the screen the camera. After that, if the camera is a PTZ camera, the operator on field can select the camera PTZ setup, and can change different PTZ, like in this example, and after that is the operator can come back to the home or the home configuration. Moreover, the operator can see the recorded camera in order to analyze the situation from field directly on camera recorded by the system. Now we can see this configuration. Moreover, we see the configuration of the workflow managed by the operational center and the remote subscriber. Now in this example, you can see the alarm coming on the operational center, the operator take in charge the alarm and start to manage. We open 2 cameras and we receive the alarm and okay, receive the alarm and you can see that the operator can analyze where is the alarm respected its position. After that, it can send the alarm and he can manage it in a simple way. Now, sorry, we are waiting for the alarm that has to come from the field. Now we are analyzing the first business case where we have an alarm coming from from an excavator, and in that case you can see that the level of alarm is 3, and we take in charge the alarm. You can see the type of alarm on the first page of the central page of the operator, and the operator can take in charge the alarm, and the operator can start the workflow to start to manage the alarm with the workflow. At this point, in this simulation, we working with the remote operator that is moving on field, that in our example is called Squadra 1, and we send we take in charge this alarm, and after that we select the people on field in order to start the collaboration with the remote operator. The operator received the notification from Android system. After that you can manage everything, and you can perform all the activity that are requested from the operational center, and we receive the acknowledge. After that, you can see on the screen that on the main screen that the activity are performed by the team on field. So the operator can stop the activity and finalize the workflow. We can close the activity. Now we have received in this moment the alarm for the impact coming from Pendulous, if I remember correctly. And now this one is a critical alarm, and this type of alarm is associated with a completely different workflow. In this workflow, we start to manage the alarm, and you can see that the first action that you can decide to do is to contact the police forces in order to coordinate an action directly on site. Otherwise, if you are not, if you analyze with the camera that it seems no alarm is available, you can proceed with the workflow. And now we ask to close the valve on north side and south side, in order to avoid any type of issue on the pipe. You ask for the pressurization of the system in order to avoid explosion or similar. And the last point, we start to use the drone in order to support flighting video surveillance. We ask to the drone system to send a drone in the alarm point that we received from the field directly. And now you can see on the screen the drone that is open the door of the hangar and are moving through the endpoint that are defined by the workflow using the coordinate provided by the alarm itself. After that, directly from the, you can see in that situation the map. You see the alarm and you see the drone icon that are moving, arriving on the final target. After that, when you arrive on the final target, the operator directly on the site or directly on the dashboard can move the camera in a horizontal way or in vertical way in order to analyze the situation in large field view or in short field view. Now we are analyzing the large view of field. In that way, we can see if someone are moving away from the target and are trying to go in some hidden place. Otherwise, I can move in vertical way. I can analyze what happens really on the target directly from the vertical side. When I finish to analyze the situation, yeah, I can define, I can send to the drone to start a mission. The mission in that case is a simple round trip around the site. In that way, I can control continuously if someone is present or are moving around the site. And during the mission, I can move again the cameras if I want in long and in short and vertical way, in a long field of view or short field of view. And after that, I can decide when I finalize all the analysis on field. I can decide to stop the mission of the drone and ask to the drone to come back to the hangar. If you want to come back to the hangar, please. In any case, you see on the map the icon of drone that are moving around the point of interest. For your information, all the coordinates related to the trip of the drone are stored in the operational center in order to be analyzed during investigation and verification phase in post-analysis. Now we are stopping the mission, and you can see the drone that are going down to the hangar. The drone are landing in this moment, you can see on the screen, and in some minutes, 1-2 minutes, we can see the hangar that are closing. When the drone arrived in the hangar, the operator can close the workflow and finalize the management of the alarm.
And now we are going to see the third type of event. And as I described before, it is a leak simulation of the event. And now the camera is approaching to the valve. The operator is opening in few seconds. Okay, we just hear the noise coming from the gas, the nitrogen, so we are complete safe condition. It lasts 1 second, just not to decrease the pressure. So now we have, let's say, some time to wait the processing of the system. And as before, we are expecting a very severe alarm, so a red alarm coming, and then the same workflow with the drone, with the possible of recalling the police, fire brigade, and also closing the valve, and also depressurize the section on the test point. Just to say that now we have just performed a test with a nipple of 0.25 inches of diameter of the hole, but in the test activity we used several size of holes, and also several shapes, the round shape and also the linear shape. So just as information, for example, just to say that today we are going to see just one of the multiple events we have simulated in the past.
A leak alarm arrived some seconds ago. Now the operator started to manage this type of alarm. This type of alarm is again a critical alarm, and the configuration of the workflow remained the same as expect on the previous one related to the impact. Prendilo in carico, vai. We start to take in charge the alarm. Okay. You have again the possibility to contact the police in order to send people of the police force on field, or the fire brigade alert. In that case, you can send the fire brigade if you see on field fire or you have the possibility to have explosion. After that, you have the possibility to ask to close the valve, the north and south valve, and to put in the pressurization situation the pipe in order to avoid any type of possible explosion. After that, we start with the drone survey. And again, you can see exactly the same situation that show. The difference is typically that the precision of the alarm in the previous case and in that case are a little bit different in terms of position, but in any case, now you can see the door of the hangar that are opening, and the drone start the flight to the final target. The command is sent from the workflow to the drone system, and the drone start the flight to arrive to the final target. During the flight to the final target, or when the drone arrives on the final target, the operator directly on the screen can see the icon of the drone are coming to the final target. After that, the operator can start to see the situation in large field of view and in vertical field of view. In this, we are start to moving start to move the camera of the drone using the vertical command, and you arrive to see what happens directly on the ground around the final target. After that, when finalized to this type of analysis, the operator decides to move decide to start emission of the drone. The drone, in that case, will move around the site in order to perform a verification of the perimeter of the site. You can see on the map that the icon of the drone that are moving, so the operator can see the path of the drone and the cameras of the drone. At the end of this type of verification, the operator can decide to stop the mission and to send the drone to the hangar. Now you can see on the screen the drone that are going to landing on the hangar. Okay. Now the drone has landed on the hangar, is closing the door probably, and when the door is closed, the operator can decide to finalize the workflow.
Okay, so just to summarize, we have seen three different events with different severity. And so the severity, depending on the severity, we saw some actions, some different actions. All the architecture of SecureGas was deployed in this test site, going from the field layer with the technologies for the detection and localization up to the diffusion to the operator and also to the public. So I hope that you enjoyed the three event and the demonstration of the excavation, the impact, and the leak detection. And so I remind you to fill in the questionnaire for the feedback and give us your support and your feedback. So I would like to thank you for the participation on behalf of Eni and also from all the other partners. So thank you again.